really kind of a neat thing that I just wanted to kind of share this with you as like another cool resource out there. So it's called Facets, and it's kind of a little project from the Google Pair team. Another part of the data preparation process is checking to make sure that you didn't collect too much of one data set than the other. Maybe the wine was really expensive, so you didn't buy as many bottles of different wines, so you don't have as many data points, and you got all this wide variety of beers, and so you have a lot of beer. And one way you can kind of see that sometimes is the charting here. The blue is, in this case, the training data, and then the orange here is evaluation data. And so making sure that your data trends are matching and evenly distributed. So in our example, perhaps something like how many examples of the two different classes you have. Maybe you would scroll down to the column, the feature that is wine or beer, and you would see something like this, and you would say, oh gosh, I have too many. So maybe you would cut down on the beer, maybe you would measure more wine, but it's something to be aware of. Just checking to make sure that your data is balanced. So once you've gathered your data and you've prepared your data in some way, you've looked at it and you've made it into, massaged it into a good form, you got to choose a model. You got to choose how you want to your system to think about, so to speak, the data set. And the kind of word art I have here is really getting at the point that there are a lot of models out there, and they serve different purposes. Some models were designed and purpose-built for images, some for sounds and music and understanding that, some better for numbers and numerical data, and others still for text and written words. So, and then I guess there's the fifth category of just structured data, your standard kind of tables and spreadsheets. And of course, that's kind of what we're looking at today. So in our situation, we have wine and beer, and perhaps we start out by just saying, let's just see if we can make a linear model that successfully can separate wine and beer, just for the sake of this thought experiment, right? And we can always swap in a different model later. And so that brings us to training. We take our model, we take our data, we bring them together. With the model and the data, we bring together and we do training. And the way you can think about training is like when you first start driving, and I know in Singapore, driving is not the easiest thing to achieve, right? Getting a car, getting a license, all that. This is my first time to Singapore, but I've been told that driving is not the easiest, thing to do. But when you first start to learn to drive or do any other kind of manual task, you don't know how anything works. There's all these controls and all these buttons everywhere. You don't know what they do. But as you learn through experience, you try out different things. And you see examples of like, oh, if I turn the wheel this much, then the car goes this far. If I'm going in reverse, I need to pay attention to these particular parts. And you gain experience. And eventually you become a fully licensed driver, and you gain more and more experience. You become a better and better driver. Maybe you crash once or twice, maybe not too many times. And you gain experience from that as well. So that's kind of the idea behind training, is you feed it lots of data, and it learns these trends. It learns how to make these predictions of wine or beer. So this is kind of the least technical slide I have, perhaps, right? So I have a more technical looking slide. More concretely, we take our training data, we take our model, and we say, give me a prediction. And it's going to probably get it wrong, right, at the beginning. And with that prediction, it then takes it, we go and compare it to the true answer, right? So the model tries to make a prediction. At the beginning, it's just going to be random. It's going to say, I'm going to guess it's beer. And then you compare it to the real answer, and you say, no, it was supposed to be wine. And so you can use that information to update your model so that next time you'll have better odds of getting it right. And so you just keep going. You keep looping through this. You push your data through, you make predictions, you get them right or wrong, and you update your model iteratively. And so that's kind of more concretely what the training process looks like. So we've gathered our data, we've cleaned it up, made it all nice, we've chosen a model, and we've trained it. But we still don't really know how good it's performing in a more holistic sense. And so once the training happens, we need to do evaluation. Evaluation looks very similar to training. Well, there's no car here, but with the evaluation step, the only difference is that we don't update the model anymore. So if you think of it in terms of like learning, like you yourself learning a new idea, maybe in school, training is when you're studying. You're learning about the new thing, and then you're updating your mental understanding of something. But then you have your exams. And during your examinations, you don't get to look at the book. You have to use your brain to recall, and then you get evaluated on how you did. And so here we take our test data. This data set is not something that the model has ever seen before, right? Just like when you take your exams, your teachers wouldn't give you the same exact problems that were on your homework or in your textbook. There would be new questions that are similar and representative. And so you take your test data, you put it through, and you yield these new predictions. And you still compare them to your test, and you can get a percentage. You can say, oh, I got 80% of these right, or 95% of these right, however many it may be. And so this brings up to the second to last step, parameter tuning, or sometimes referred to as hyperparameter tuning. So here, this is kind of more of a placeholder slide of like a reminder to don't forget to do this step, because not every time you train, you'll get the most optimal results, right? Just like not everyone is the best driver ever. There's lots of criteria, lots of conditions that impact and influence how good the resulting model becomes. There's lots of kind of different parameters, knobs and switches that you can adjust. And a lot of times what you'll do is you will set these values at different values and then run training in parallel. You'll just train multiple copies of this model with different parameters set, and then have the output that you can then evaluate and see which one of these many models that I just trained, same model, just different parameters, which one of those did the best. And you can do that iteratively as well. And so a lot of times, folks, this can like take a while, especially for like more complex models, just because there's a lot of knobs to tune. You can adjust a little bit, do a bunch, see how it is, and then come back and tune some more. So it's almost like you need machine learning to learn these parameters for your machine learning in some cases, right? And that, well, that's a separate talk. So this brings us to our last point. Finally, we get to use our model. We got to make predictions, right? So we'll take a new sample. We'll probably need to go to the grocery store again and pick up some more alcohol, and then you can feed that into your model and get a prediction. And hopefully, you get something that is accurate. So that's kind of my silly thought experiment about how we can think about machine learning and these kind of steps and workflow. Let's now kind of walk through and highlight some of these in real code. I'll pull up some real TensorFlow code, and we'll see how this kind of matches up to these steps, and we'll walk through that workflow together. Pausing for photos. Okay, so first, I mentioned TensorFlow. I just want to take a poll. Who has used TensorFlow in some way? All right, decent amount, awesome. So people who didn't raise their hands, those folks who raised their hands, they can help you answer questions you may have about TensorFlow and get you going, because my flight is tomorrow morning. So, and one of the things about TensorFlow, right? TensorFlow is Google's machine learning library. It's an open source tool that I primarily like because it's useful both in prototyping and in running in real production systems. You don't have to change your code. You don't have to rewrite your machine learning code to make it work in production. Now, for those of you who haven't worked in, well, it's not flashing on my screen, so yeah. For those who haven't done a lot of machine learning before, this may seem odd. Why should I have to rewrite my code anyway? That doesn't seem like much of a feature. Like, once I write my code, I should be able to deploy it. That's typically, in most of software, how things work. You are writing for production all the time. But historically, working in machine learning involved using languages that were good for prototyping, iteratively fast, but not performant at scale. And so after you proved out your algorithm, after you did some work, then you would re-implement the entire thing from scratch in a different language, like C++ or Java. So with TensorFlow, you don't have to do that anymore. Part of the reason for that is it is built on C++, but the API is in Python. So you get the speed of C++, but the readability and ease of maintenance of writing Python. And the name TensorFlow comes from combining tensor and flow. Tensors are arrays. They're just multi-dimensional arrays. So you can take one long array, then you have a square, then you have a cube, and then a hypercube, et cetera. And you're going to flow these numbers through a graph, a computational graph of operations. So I have a super simple example of a graph here. We're adding 2 and 3 together. And what happens is the inputs get pushed into this addition node, and then output is a 5. The notable point here is that in order to make this work, you have to have the graph pre-constructed. You have 2 placeholders for the inputs, and then a place for the output, and of course our addition operation. And then we push our data through. So if we think about our previous example with the wine and beer, we would have our model in place, our graph, and then we would have our data collected separately. And then when we bring the 2 together, that's when we flush all the data through the graph and do the training and yield predictions. So this is like my analogy for that, but on a much smaller scale. And one of the neat things about TensorFlow is that you can write this code once in Python and have it run on many platforms. So there are some you might expect, CPUs and GPUs, but it also runs on Android, iOS, and even Raspberry Pi, which for me is really exciting. I have a couple of Raspberry Pis at home. You can tinker with it and do various like IoT and maker stuff. One of my colleagues hooked it up to like little flexibility sensors to a glove. And so then he trained a model to understand like rock, paper, scissors, right? So just based on the fingers, each finger had a flex sensor, and then you could like predict which one, just like as a silly experiment. And that's one of the things I try to encourage folks to do is take TensorFlow and play with it, have fun with it. It doesn't have to just be a tool, an academic tool. It doesn't have to just be a hammer. It can be a soft plush hammer too. So we mentioned that TensorFlow runs on C++ at its core. And at its core, it's also a distributed execution engine. This means that when it comes time to scale, you can take that graph and duplicate it across many worker machines and have it execute that fast C++ at scale across many machines. And on top of that, we have our Python front end. Now, even though I say Python here, you can tell there's lots of space in my slide. And that's because there's more layers on top. Because the Python front end at this level is still fairly low level in terms of TensorFlow. You're building graphs manually. You're doing the 2, you're doing the 3, you're adding them together. And we can make it even easier, is the good news that I bring. So on top of the front end, we have layers. You can build models from scratch. Whatever models you can dream of, this is like reasonably low-level building blocks. If you don't want to be building the building blocks, well, we can use the building blocks. And then above that, we have entire essentially pre-built models called in the Estimator library, or you can use a Keras model. Who uses Keras? Anybody? All right, we got some Keras folks here too. So Keras has great integration with TensorFlow in that you can use it to, now in TensorFlow 1.4, you can do get estimator. You can get an estimator, right? This is this other library in TensorFlow, from your Keras model. And what you get with that is you get distributed training, because Keras supports single core, but single thread, but then with estimators, you get all the niceties of fast distributed execution. So even there, though, you're still using your own models. And within estimators, there's also this notion of canned estimators. So this is truly, it's pre-built for real this time. And you can just pass in some configuration parameters rather than having to really build anything from scratch. And so this is where I recommend people to start, with canned estimators. Use that. If it's good enough, awesome. You're done. It'll scale. It'll run distributed, and the code will be short, clean, concise, easy to maintain. If you need more flexibility, then you start going down the layers. So here, let's look at an example in code. This is a canned estimator. It's a deep neural network, hence the DNN. And deep neural networks have many layers in them, and the layers are all connected together. So if you just imagine with me for a moment, remember the graph of 2 plus 3 equals 5. Imagine having many layers of operations and trying to wire them all together because they're all connected to each other, right? So the code for that would get really messy really fast. And instead, we have this canned estimator that's done that for us and done it right, which is awesome. And all we have to do is supply some numbers. So here, the hidden units argument is the number of nodes, number of neurons per layer. And so in this example, we have 4 layers. The first layer is 1024. The second layer is 512, and so on and so forth. So if you decide, I want to experiment with a 5th layer, then great, comma 64 or comma 100, whatever. If you decide, I really don't need this huge layer at the front. Okay, backspace, 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 backspace. Okay, I'm done. So the ability to just play with this and experiment without having to completely rewrite chunks of code is really, really nice. And for the machine learning experts in the audience, yes, there are other arguments as well. It's not just those 2 or 3 arguments. You can configure lots and lots of things. Okay, that's just a brief mention of that. I don't want to overwhelm folks who are seeing this for the first time. Okay. Now let's do this for real. This is just as exciting as wine and beer on a Friday night. It's census data. Okay, so this is from the 1994 census. We got about 32,000 training samples, 16,000 evaluation examples. So, even though I have thousands and thousands of examples, it's still small enough to fit in memory. So we'll do this locally on my machine. And this was extracted from the task. Yes, the task that this data set is kind of geared toward training you to answer, put it that way, right? This is very much a toy data set. It's meant to be an example to help you work through the code, and then you can swap in your data set. And you want to predict whether a household has above or below $50,000 in annual income. And this last column is actually a string, and it's not 0 and 1. It's kind of a mess, so we'll see that. But first, let's look at some of the other columns. The data set has, I think, like 12 or 13 columns, and they're what you'd expect. Things like age, education, what your occupation is, as well as things like hours per week that you worked, and then, of course, finally, this income bracket, above or below 50,000. And you can see here, I bolded it here to make the point that it really is literally the string less than 50K or greater than 50, and then less than equal 50K. Could have just given us zeros and ones, but that's just me. All right, let's see what it looks like in code. And that's facets. Okay, so this, the first bit here is just running TensorFlow, loading in TensorFlow. So this part, right, it's just import TensorFlow. Everything else is compatibility layers. So the top part is so you can run it in Python 2 and Python 3. I'm pulling in NumPy just because it's a useful thing to have to process numbers. TensorFlow will by default log at the warning level. I like to log out info so I can see everything, but sometimes I regret doing that because there's too much output, so your mileage may vary. One thing I do like to do is print the version of TensorFlow I'm using, because I deploy my code locally. I run it in the cloud. I run it all sorts of places, and it's useful to have a print statement that says, this is the version of TensorFlow that is loaded and running right now, because sometimes it's not what you think it is, and if it's not and you don't know it, bad things can happen. So it's like a useful, just like cheap line that is easy to write but can really pay off. Next, I have some column names. So this is just for loading in the data. The data happens to be a CSV file, so that comes with it all the things that you need to do to load in CSV files. Who here uses Pandas? We have a fan. So Pandas is great, right? It lets you really easily load in data and kind of inspect it and play with it. So I really like to just load it in real quick with Pandas and see what comes out kind of the other side, if you will. And so once you have that, and I'll usually play with that a little, you can use what's called an input function. So TensorFlow, we talked about how you got to bring your data and your model together. And the way you bring your data and model together is with an input function. The job of the input function is to take your data, do whatever it has to do, and push it onwards and return it in a form that the model can read. So in our example, we're going to, again, load in that CSV. We're going to apply a lambda to turn the terrible, terrible string column into zeros and ones. So I'm doing true, false, and casting to an int. Best practices. And then deleting an unused column that's like was used for the statisticians. And of course, I also end up deleting the label column because I've already saved that off as labels here. And so then we have our X, our data frame, and our labels Y. And we pass in batch size, epochs, and shuffle. So batch size is the number of samples that get pushed into the model at once. So in our example with the beer and wine, you might have like 10 examples of different beer and wine, and then you load that in, and then it does the crunching, it comes back and updates, and then do 10 more and updates. And batch size is one of those, actually all three of these, well, except for the shuffle. Batch size and epochs are all considered hyperparameters that you can tune down the road, because whether you pass in 10 at a time or 100 at a time makes a difference, believe it or not, on how well the machine learning system will train, how good the accuracy can be. And epochs is referring to not epoch time, but the number of kind of rotations through the entire data set that gets shown. So for example, if you have 1,000 different records, one epoch would be you train on 1,000 with no repeats and stop. Right? 2 epochs would be go through twice. And then shuffle is whether or not you shuffle. So that's just true false. And so you notice I have this pandas input function. And this is one of the TensorFlow kind of utilities. There's also a NumPy input function that will take in NumPy arrays. And the arguments are essentially identical. X is a NumPy array instead of a data frame. That's it. So yeah, I find these really handy because you can write your own input functions, but if you can fit it into pandas, data frames, or put it in a NumPy array, this just makes it way easier, because writing batch and epoch semantics and getting a good shuffle in, like, you can do it, you can figure it out, you're all good engineers, but it just saves you some work and it's a lot more readable. So input functions join together the data and the model. So now we're going to move on to the model. We got to put our model together. We saw earlier that we can just call one line and make our model, but that's just the model architecture. We still need just a little bit more that needs to go kind of in front of the model or on top of the model that helps specify what the structure of the data coming in is going to look like. Which columns are strings? Which columns are integers? Which columns are something else crazy, right? And so those are called feature columns. Each column of your data is a feature, and so they just, I guess, expanded it to feature columns. And there are 2 types of data in our data set: sparse and dense, or categorical and continuous. Categorical ones will tend to be strings, but they don't have to be. And they're usually columns that have a finite set of known unique values. In this particular data set, there are 2 distinct values in the gender column, male and female. And so we can specify that using categorical column with a vocabulary list. And I did it for another column, and then I kind of got lazy and decided to use categorical column with hash bucket. These will generate your values for you, so then you don't have to type them out by hand. Imagine if you had 41 unique values in a given column, and you had to, you could type it out, you could put it in a file, you can actually pass in a vocabulary file, but if you have 1,000 columns, and some of those columns have 1,000 distinct values, architecting that can be a bit of a pain, especially if you're just starting out and trying things. So you can just say hash bucket size equals blah. And usually what I'll do here, I'm not showing it in this example, but what I'll usually do is I'll pick that column out of my pandas data frame and call dot n unique, and that's the count of how many unique values there are in that column. And so with our columns configured, at least our categorical ones, and these are kind of the 2 techniques that I'm showing here, vocab list versus hash bucket, we can move on to the continuous columns. They're a little more straightforward. You just say numerical column and you're done. Give it a name. So these names match the column headers of the CSV file. And you'll notice, again, that these feature columns are not directly tied to the data explicitly. They're just names. I just gave it a string, saved it to a variable, and called it a day. So these will go on top of the model. They're just configuration for the model. And later the input functions will bring the data in, and this way now the data knows where to kind of insert into the model. The age column will go into age, the hours per week will go into hours per week, etc. So that's kind of why feature columns have to exist, because the model by itself doesn't know anything about your data set or its structure. And then we can, before we get to go on, there's one extra piece that's fun, is you get to do transformations, if you wish. You can take a continuous column, like age, and you can break it into segments, into buckets, manually. And you can say, I want to think about age not as a continuous spectrum, but as groupings, right? So you can just give the boundaries, and you can have, now you've turned this age column into a categorical column. So the categorical column, now you can take that, if you want, and you can cross it, age buckets, with other categorical columns. So you can start combining different categorical columns together. And this is where you, as the data analyst or the data scientist, can exercise your domain knowledge of the particularities of your data set. You know column A and column X are related in some way. You suspect that they have something to do with each other. And so you can say, I want you to cross these columns together and yield an extra column that are these two columns crossed. It's like this and that. And in some cases, it could be this and this and this and that all together. And this is kind of the stuff that sometimes folks respond to with saying, isn't machine learning supposed to solve all my problems for me forever? Right? Here, yes, in theory, deep neural networks are supposed to find these kinds of particular relationships. If you have enough data, if you wait long enough, and then wait some more, eventually you might be able to tease out some of these relationships. But if you already know up front that this is a reasonable likelihood of these columns being related, why not put this one-liner in, see if it works. If you don't like it, you can delete it and run it again, because all the pieces are kind of very compartmentalized and separated. And so with the, feature crosses and the transformations, this is optional, but can be fun and is something that you'll end up having to tune down the road. These are more hyperparameters. Sorry, there's a lot of them. And so we'll take all of these columns, we'll group them together. We'll take all our feature columns. In this case, we're kind of grouping them together into the categorical ones and the continuous ones, only because the model that I'm using is doing that, but you don't necessarily have to do it this way. And so this gets us to the interesting part of creating our model. So this is the simplest case, using a linear classifier. So the classifier part is just referring to the fact that we are separating between two or more different classes of results. And so we'll put in our feature columns, in this case, the wide columns, because linear networks are sometimes thought of as wide networks because the data that comes into it is wide. There's lots of different types that go in, and it all enters as one kind of wide array rather than being represented in a more compact form. And alternatively, so say you do the linear network, and you look at your results, you do the training, right? We're going to kind of jump ahead in our time frame, and you say, I'd like to try a different model. Right? I regret my decision in the choosing your model step, and I want to go back. Hopefully that means, gosh, I hope I don't have to rewrite all my code or change a whole bunch of things to make this work. Well, I have good news. You just have to change the model, right? You want to change your model? Okay, change your model. Don't rewrite anything else. And then maybe later you hear about this interesting other thing that takes the deep model and the wide model and combines them into one supermodel, and it's a really long name, but you copy paste it instead of typing it because it's a really long name, and see if that works for you. And again, you don't have to rewrite any other piece. So training your model, and this is basically code that you will only have to write once or copy paste once. You call train on your model object, and then you pass in your input function and let it run. And when you change your model or when you change your data set, this line doesn't change. I mean, I guess it doesn't hurt that it's only one line to run training, so it's not really much of a concern either way. And then once you do your training, what are you supposed to do next? Evaluate. So here it is, m.evaluate. And you pass in your input function, and you pass in, well, not much else. In this case, I've got a bunch of parameters here because when you're doing evaluation, we wanted to assess the accuracy of stuff, right, without any additional updates to the training. So what we would want to do is use our test file, not our training file. We would want to only go through the data one time. And we don't need to shuffle it because we need to go through all the data anyway and just compute that accuracy score. And so this will return to us this function that does that, that will return all the data one time in order and then stop. And so that will give us our accuracy. And if I'm starting to sound like a broken record, making predictions also uses an input function. Because anytime you want to shuttle data into your model, you need an input function to facilitate that. And partly, that means we can have the input function do any data manipulation you need to do, or call out to distributed data storage libraries to pull in that data. So here, I've just taken the, we lost the spot. Okay, well, I'm just taking 5 random, I just picked a random number, 5 random rows from our test data set, and I'm just going to use that as our input. That's our kind of data predict, right? And I'm going to pass that in as the x argument in my input function and pass that through. It's just like test, right? Number of epochs once, no need to shuffle. Actually, you don't want to shuffle, otherwise how will you tell which one's which, right? You want them to be in the same order, so you can check it on these 5 and get your predictions. So here, you call .predict, sensible name, and pass in your input function. And hopefully you get your predictions back, right? So that's kind of the workflow of using TensorFlow's high-level APIs to do classification, to do machine learning in a flexible, compartmentalized way on structured data. Oh, not this tab, that tab. All right, and I should also mention before, as we come near the end here, TensorFlow has something else built into it. Can I get a show of hands? Who uses TensorBoard? Got 3? 3, yeah, that's all-time high, no. TensorBoard is part of TensorFlow's open source release, and it's a visualizer, as you can see. And when TensorFlow does its training, it outputs event files, or like one event file with lots of events. And these events TensorBoard lets you chart these events and view how things are going. It also lets you see the actual graph that was made for you and zoom in and expand pieces. It also, if you're working with images or text or sounds, you can actually see those in here too. And you can see on the left here, I've got this scrolly bit, lots of different models and graphs kind of laid over on top of each other. So you actually would supply TensorBoard the top level directory where all your models are being stored, all these events are, and it will just recursively search down and display all the different events it finds, event like series. And so then you can compare different models side by side visually, which is really, really nice. Because before that, I was writing down the accuracy from my models on paper in a notebook that I lost. So use TensorBoard. It is your friend. Oh, fun fact, TensorBoard starts up a Python server on your local machine, and then you go to it, you navigate to it on Chrome or in your web browser, and you go to localhost port 6006. Would anyone like to guess why we chose port 6006? Yes, it spells Goog. Right. All right, so that's TensorBoard. And if you want to play more with kind of machine learning in a slightly different context, this is a fully web-based JavaScript neural network playground. You can see here, there's a plus and minus. I can add more layers. I can add more neurons per layer. I can choose different data sets on the left here. And we can see kind of, here I've separated the blue from the orange. And so that's a lot of fun. And across the top, you can see there's some crazy words here about learning rate, activation, regularization, et cetera, that we didn't get into today. But those are some more hyperparameters that you can try playing around with and seeing how it impacts your results. So that's playground.tensorflow.org. And finally, a personal plug, I've been working on a series of videos called Cloud AI Adventures. It's on the Google Cloud YouTube channel, and each week or two we release a new episode. I try to go explore one particular interesting facet of machine learning or kind of AI and some of the tools and kind of the science behind machine learning to try to help you guys learn stuff. And so yeah, if you like it, whoa, it's really big. Okay, I just noticed myself behind me. This is a big screen. And yeah, and if you guys have things you're curious about, please tell me, and then I can make episodes about it. Right, I can help answer those questions. And you can reach me on Twitter. I'm at Yufeng G. And the code that we looked at today is at wide-and-deep-census. And if you want an example of how you can leverage this for your own data set, for example, I have another sample called wide-and-deep-code, which takes basically the same code, but applies it to a different data set. So you can compare and contrast these two and look at how, A, I didn't have to change that much, but B, what did I change, right? So then you can put in your own data set and kind of copy the edits I made to make that transformation happen for you. And so with that, I think we're just about right on 7:45, that timing. We have 1 minute for questions. I don't know, where are the organizers? Oh, question in the middle, great. Can you give an example? What do you mean? Okay, so the question is whether or not TensorFlow is looking at doing things with non-neural network-based approaches. The linear classifier is not a neural network, but also there are I think Bayesian classifiers, k-means, KNNs. They're all in there as well. So while TensorFlow was built originally for the express purpose of doing easy to code, highly performant deep neural networks, or just neural networks, I should say, neural networks in general, it also contains all these other pieces. So you can kind of stay in the same tool set. You can learn one tool and not have to be limited in what you're able to do. And at its core, especially if you go down the layers, you eventually reach, basically, it's just like a math library. There's examples of people kind of using TensorFlow to do just math, raw math computations. It sounds like you have a math background. Oh, this mic is dead. Okay. There's an example of, if you're familiar with the Mandelbrot set, by any chance? Yeah, there's someone who did a visualization of that, computed it from TensorFlow. It's pretty cool, and there's a guide for that and such. So yeah. Other questions before we bring on the next speaker? Going thrice. Okay, sold. Thanks a lot, guys.
Okay, so we have some slight AV issues, but in the meantime, I would like to introduce my co-presenter. Her name is Boo. She traveled with me from San Francisco, and she's very excited because she just got her Google Doogler badge. So it's her first time that she's been at a company that's given her a work badge. So she's very, very excited to be here. I don't know. So there is something incredibly awkward about watching the presenter before you. It's not quite like wearing the same dress, but you actually brought the same sample data set to the party that I did. So I will be showing you how to do the same different machine learning techniques, but with the same sample data, which is just a little bit awkward. Not as awkward as the broken AV. I can do like an interpretive dance to represent. Ooh, is that working? Okay, I should probably take off my Hello Kitty sunglasses, make this more professional. Damn it, no, okay, that was some misplaced optimism right there. Yeah, okay, cool. So in what does not normally happen, we're gonna try switching to a Linux laptop for a second. Hold on.
When your Mac doesn't work, use your Linux laptop. Things that no one says.
It looks like my laptop actually suspended correctly, so the battery is not completely dead, despite running Linux. That's a pleasant surprise.
If you remember, tell them what TensorFlow stickers at the end. But I heard that meaning, which is a problem, so maybe we should.
That's all right. Let's see if this actually works.
Oh, that's not a USB port.
Okay. Does it detect? No, it doesn't detect on this display either.
So it's not my laptop's fault.
No.
Vindicated.
I mean, the odds that a Linux laptop was going to work when the Mac one wasn't is pretty low. So I'm curious, who has experience with Apache Spark? Is that 3 people? 4 people? Okay, I feel like that's not a... Who has no experience with Apache Spark? Yeah. Okay, cool. So those 4 slides about what Apache Spark is are going to be really good slides. But in the meantime, I can just sort of talk about what Apache Spark is and how it works and how it's different than some other distributed systems. So how many people are familiar with MapReduce? I see mostly the hands that I saw for familiar with Spark, so that's not going to be a very useful description. Okay. So Apache Spark is a distributed system, and it's a general purpose distributed system, which means it's not just for doing SQL or just for doing machine learning. The idea is that it's for sort of doing pretty much whatever it is you want to do. I'm talking about machine learning tonight so that we stay on a consistent theme, although it's maybe I will be talking about machine learning, I hope. But Spark is really cool, and you can run it in a variety of clouds, of course, including Google's cloud, which, yay, please buy things from my employer. They pay my salary. But Spark takes a really different approach to resiliency than other distributed systems. A sort of classical approach to handling failure in distributed systems is writing your data out to a bunch of different machines in case something goes wrong. And so this is really important because when we're running on a single node or 2 machines, we might have 2 machines fail, but we can just restart the machine. That hasn't worked tonight, but normally, you know, if one of the machine fails and you're working on your own, you can just restart it. But when you're working in a distributed system, if you have 100 computers and every time one of those 100 computers fails, you have to sort of restart everything, it's going to go about as well as this talk is going. And you just won't ever really be able to get off the ground. And so Spark takes, resiliency is really important, and Spark takes a different approach to resiliency. Rather than writing the data out to a bunch of different computers, so if some of them goes away, it can just go and ask its friends for it, Spark says like that failures happen, but they don't happen all the time. Like computers tend to be more reliable than these 2. And Spark builds up this graph of operations, pretty similar to the TensorFlow graph that was being talked about earlier. But instead of being a graph of like necessarily mathematical operations, it can be a graph of like lambda expressions or sort of arbitrary transformations. And Spark is lazily evaluated, which means that it's kind of like a teenager. If you ask them to take out the garbage, I don't know, maybe people are nicer over here, but back in Canada, if I ask someone to take out the garbage and they're 16, they'll assure me they've taken out the garbage until I actually go and check and realize that they haven't. And Spark is like this teenager. You can ask Spark to like, you know, do all of this work, compute all of this data, and Spark will go, yeah, for sure, I've got that. And it's only once you actually force Spark to save the results out to a file that it actually does this work. And this is really interesting because what it means is that Spark builds up this graph of operations, and this is used for the lazy evaluation, but it's also used for resiliency. And so because it has this graph of what you've asked it to do, if one of the computers fails while it's computing the work, it just takes that piece of the job that was responsible on that machine and reassigns it to another machine. And this is really nice because it turns out that writing data out to disk is kind of slow, and writing data out to 3 different disks over our network is incredibly slow. And so sort of the classic techniques that we use in distributed systems to achieve reliability were very reliable, but they were very slow. And so by sort of flipping this on its head and just treating failure as a first-class citizen, but like finding a way to do that quickly, allows Spark to be a lot faster than traditional, than traditional systems have been before Spark. And so Spark is really awesome for a bunch of reasons. And one of the things that I think is often overlooked about Spark is that it supports a wide variety of languages. Are there any Python developers in the house tonight? Yay! Are there any Java developers? Many less people. Okay, and this is kind of a long shot. Are there any Scala developers in the house? 2. No, we can be friends later. Hi. Okay, are there any like hardcore R developers in the house? Okay, there's one really excited person and one kind of non-committal person up at the top. And I'm getting like flashbacks to the early 90s right behind me. Did we just do with the turn it off and turn it back on thing?
So guys, we are just restarting the system for a bit. So this is a quick 5-minute break. Yeah, before we resume the fun with Holden, just give us that quick amount of time to get things right. And yeah, you won't be missing out on the Spark's machine learning network for too long. Yep, apologies for this. So just 5-minute break. Yeah, and then after that, we resume the topic.
Okay. Yay! This still works. Okay, that's awesome. So I'm going to talk about how to do machine learning with Apache Spark, which is, maybe not as cool as TensorFlow. But it's kind of neat because you can do a bunch of other things with Spark as well, which TensorFlow is maybe not as great at. And so if you're doing your machine learning as part of a larger pipeline or part of a larger project, it can be kind of cool to do it in Spark. The examples from today are mostly in Python, except for the one example that's in Scala at the end that I did not have a chance to rewrite because I'm really lazy. Yeah, next slide. Maybe, clicky. Button. Yay! Okay, cool. Sorry, the AV success early in the evening has set a wonderful low bar that we can hopefully get over. So my name is Holden. My preferred pronouns are she or her. It's tattooed on my wrist. I am a developer advocate at Google, which is lovely. They pay both me and Boo money. Boo is saving up to buy some new toys to play with, and I am trying to pay rent in San Francisco. I am a Spark committer as of January, but what I say is not necessarily the views of the Spark project or necessarily the views of Google. They're my own sort of views from drinking too much coffee and living in a windowless room. Before I worked at Google, I worked at IBM, Alpine, Databricks, Google, Foursquare, and Amazon. I'm a co-author of a few Spark books. I got a much better royalty deal on the second one, so I think this is the one that everyone should buy. The first one is maybe more useful, but I don't get nearly as much money. You can follow me on Twitter. It's just my name, and the slides will go on SlideShare. And we're going to go to the next one. So outside of work, I have a bunch of things going on. I'm trans, I'm queer, I'm Canadian, I'm part of the leather community. And this is just really to remind people that we all come from different places. We all have different backgrounds. Some of us are perhaps more visibly different than others, but we should all be nice to each other. And if we all work together, we can all get through this really kind of terrible stuff of dealing with out-of-memory exceptions together, and we can come out on the other side with really shitty startups. Okay. Not this part. Yay! Okay, right. And as I already introduced, this is Boo. She's very important. And she's also on Twitter at Boo Programmer. Her books are limited edition runs, though. You can't buy them on Amazon. It's very unfortunate. And the clicky button now works on its own. No, it doesn't. Oh, you just look at you could have convinced me completely. So I'm hoping you're all nice people. You probably care about ML. It looks like probably not a lot of people know Spark, and that's fine. I do have some slides about that. Clicky button. Yay! Okay, we're going to talk what Spark is, how it sort of works. We're going to go through the industry standard word count example. It's a licensing requirement, which is why it's in every big data talk ever. Also, there's some legitimate reasons what's happening. Okay. I have a different clicky button. Is this one going to work? Clicky button. Okay, shiny. I'm really excited by simple things today. We'll talk about how Python works, and then we're going to focus on how to do some machine learning in PySpark. And that's hopefully the part that you all came for. There's also cat pictures, lots and lots of cat pictures. Right, so there is an example. I did use the same data set. I'm really sorry. We should have talked beforehand. I would have chosen a different data set. We're going to build a decision tree. A decision tree is not nearly as cool as a neural network, especially not a deep neural network. Although it turns out when you have 50,000 examples instead of 2 million examples, a decision tree probably is actually what you need. But whatever. There's an optional homework section. I am leaving Singapore tomorrow at 10 a.m., so I will not be checking on people's homework, but I trust you will all do it. And you can run this stuff on Dataflow, yay, or Dataproc, whichever. I get our products confused. Which one runs Spark? Does anyone know? Okay, you can run this on Dataflow or Dataproc. I'm sure we sell both of those. And one of them will run the examples from tonight. I don't remember which one. Yay! Okay, so there is a small companion Jupyter notebook. If you're interested in sort of playing around with this code afterwards, I'd encourage you to go there. You can install Spark on your own as well. This works too. Yeah, IBM Bluemix, Databricks Cloud, anyways, everyone sells a hosted notebook solution. I think we sell one too. It's good. Okay, here's a cat. Okay, not everyone has fallen asleep yet, so that's good. Right, so what is Spark? Most people come to Spark in sort of one of two paths. There is the path of, I have a MapReduce job, it's taking 16 hours, what am I gonna do with my life? I'm kind of bored. And those people search for how do I make my MapReduce tasks faster, and then they find that like, ooh, wait, okay. Then they find out that Spark can be 100 times faster than MapReduce if you believe vendors. Never believe vendors, especially not me, but it can be a lot faster than MapReduce. The other reason that people come to the wonderful world of Spark is they find that their Pandas data frame no longer fits in memory. And this is both happy and sad normally. Normally your data frame doesn't fit in memory anymore because you have a lot of customers. That's exciting, but it's sad because now your job has become harder. And then you come to the wonderful world of distributed systems and sadness. And then you have to work with Spark. Yay! So it's general purpose, as I already said. One of the things which is important to note is it's an Apache project. And this means that like I work on Spark at Google. I have many former coworkers who work at IBM on Spark. I have some former coworkers at Databricks who work on Spark. There are even people that I haven't worked with who work on Spark at Yahoo and other places. And so this is really useful because it means that like you don't have to worry about one of the companies deciding that they don't care about it anymore. There's a lot of people who all sort of work on the same project together. And this is really cool. It also has Python APIs, which I think is really important because a lot of the traditional big data tools are really Java focused. And Spark is more focused on allowing everyone to work together, especially Python users who are very close to my heart. Yay, okay. And we can see this fine architectural diagram, which illustrates that I do not have a designer working with me, and I have not found the Google slide templates, which are much nicer than the default ones that I can get. Yeah, and there's two core abstractions in Spark, and they're sort of cut off by where the podium is, but one of them is called a resilient distributed data set, and the other one is just called data sets. And despite how they're named, the resilient distributed data set is the basis of data sets, rather than the other way around. It's very confusing, but don't worry, it just gets worse. So Spark has a bunch of different pieces in it, and I think this is really important. It's not just a machine learning framework. I mean, machine learning certainly brings in a lot of money nowadays, and so we definitely have a machine learning framework, but we also have a SQL framework, we have some streaming frameworks, we have a bunch of different language APIs. These are important because not everyone wants to learn Scala or Java, or even some people don't want to learn Python for reasons that escape me, and that's fine. It has a collection of graph tools. None of them work, but they're very lovely. And I'm sure that one day they will work. We also have a second machine learning package because why do one thing well when you can do two things poorly? And we have a collection of community packages. And that's just a nice way of saying everything that I forgot to put on this slide. And yeah, that's pretty much Spark. Right, so at its core, Spark exposes this thing called a Spark context. And this is sort of our entry into the world of distributed systems. We can use it to load data in. We can do a bunch of other things with it. The Spark context is where we are going to do a lot of our configuration. Conveniently, if you're working on your laptop and you don't yet have a cluster available to you, although it's really easy to get started with Google Cloud. Please pay me. Master can be local, and that just means that Spark will run against local mode, and it'll set up actually sort of a little fake distributed cluster on your machine for you. If you've got on-premise, you probably have a Yarn cluster or a Mesos cluster or something of the type, and Spark can also connect to those types of clusters. Right, so Spark's core distributed basis is this thing called an RDD. And in many ways, we can just think of an RDD as being like a collection. The only problem is that abstraction breaks as soon as we try and do most things with it. We can't index into the collection. And we can't really do anything useful. But it's a distributed collection, and it doesn't exist, and that's great. But it's partitioned, which means that once your data actually does have to exist, which will only happen under very specific circumstances, Sparc will split up the data on a bunch of different computers. This is really useful. It will also split up the work on each of these partitions, and it recomputes on node failure, which is what I was saying when I was doing that sort of improvisational bit with no slides. This is really useful because recompute tends to be faster than having to write your data out a lot, especially if you're running on a bunch of 486s. Yeah, your computers are going to fail all the time, but we don't run on 486s anymore. Sparc's new fancy thing that replaces RDDs are called data frames or data sets. If you're coming from the Python world, you might be really excited to hear that there's distributed data frames, although most people do not look very excited in the room today, so perhaps you're not Python users, despite raising your hands earlier. So they're also distributed collections. They have the same resilience mechanism. They use recompute. The thing is, they're not really data frames in the way that you're used to thinking about them. They really have none of the functionality that you want. But they have just enough functionality to get your job done, which is really annoying, but it's better than nothing. So like a lot of the really cool statistical features available in Pandas data frames aren't directly implemented in Sparc data frames, but it gives you the primitives to do many of the computations that you want to do. Data frames are only runtime typed, also known as Python. Data sets are Sparc's Scala API, and they're compile time typed, and they're very fancy and nice. They do some really cool things for performance, where if you write certain operations in Python, it will actually evaluate those operations inside of the JVM, which can be a lot faster. It can't do this for all operations, but this can happen for a lot of things. This is nice. Okay. So we have our mandatory word count example that must be included in every single presentation. And so here we can see our Sparc context is called SC. And this is, if you run the Sparc shell or you're using one of the hosted notebook solutions, the Sparc context will be created for you with all of the properties that you want configured on it. And here we say that we're loading in some text data. And this text data can be in HDFS, it could be terabytes of data, it could be on our local file system and literally kilobytes of data. It doesn't really matter. And then we can write sort of arbitrary lambda expressions. And this is part of where Sparc's general purpose nature comes in. We can do whatever we want here. Here, our lambda expression is tokenizing with spaces. This works very well in North America, where I live, and I get to pretend that this works well when I travel. You could use actual fancy, like spacey tokenization inside of here if you wanted to really do a proper word count, but you don't have to. And here we can see we take the words, we pair them with the number 1, and then we take each word. So reduce by key just combines all of the things with the same key, and then it applies this lambda function. And the part which is interesting is, oh, no, clicky button. Okay, yeah. Until we actually run this line, Sparc hasn't done anything. And this is really cool because in a distributed system, if we eagerly evaluated each of these steps, I would be going over my data many, many times. And this is a thing which happens in sort of classical MapReduce and other things. And so by saving the actual computation until an action occurs, Sparc is able to pipeline all of these operations together for the most part and reduce the number of passes it has to do over our data. This is kind of cool. Word count is kind of boring, but that's okay. Here's some ways to tell the difference between like transformations and actions. Transformations are things which, when you run them on a data frame or an RDD, they give you back another distributed collection. So mapping or filtering, these things are sort of classical functional programming techniques. The alternative is things like counting or saving the results out. These things we can't put off. We can't do them lazily, so we have to evaluate them eagerly like an eager beaver. As a Canadian, I like the beaver example, because beavers. And then pandas are inherently lazy. Okay, well, anyways. Man, I'm used to having my slides in front of me. I'm sorry. So how can we tell the differences? Transformations are lazy, actions are eager. Whatever. This isn't super important. We're going to go and do how Sparc works. Yay! So in America, this is called a lawsuit because children will die. But in the rest of the world, this is called entertainment, including Canada, because children will die. So why lazy evaluations? I talked to this a little bit. Pipelining procedures allow less passes over our data. This lets our stuff be faster. And another important part is because RDDs never have to really exist, we can have these intermediate steps which would actually be too big to fit in memory, but provided that we have a reduction occurring, it's okay because the intermediate step will never fully exist. It'll only sort of partially exist, and it'll apply the reduction as we go. This can get a bit confusing because it's not always true, but essentially until you get an out-of-memory exception, don't worry about it. There's some magic happening behind the curtain. To find out more, you can buy several copies of my book. Sleeping on top of it definitely teaches you more about Sparc. So what happens when we run our word count example? We've got this cloudy thing. I should probably replace this with Google Cloud Storage instead of HDFS. But you can connect to sort of whatever you want. This is where your data lives. You've got a bunch of worker nodes, and then you have this driver node. And the driver node is the part where you're running your Jupyter notebook or whatever your preferred interface is. And these are all of the things where you're giving me money. Or someone money. Anyways, so our driver takes our function, it sends it out to the workers, then the workers go over to the cloud, and they read some data in, and then they go and they compute some stuff, and then if we wanted the result to come back to the driver, for example, we were counting some stuff, we would send a summary of everything back to the driver. We might also have the workers do some work and write it directly back out to the cloud, but that's pretty much a good example. So we're going to go ahead and we're going to load the same sample data. This is really not all that exciting. Loading CSV data is kind of boring. But there's actually some really cool parts that can happen inside of Sparc's data loading. Does anyone work with JSON data by any chance? Okay. Of the people who work with JSON data, how many of you know the schema of all of your records? That is 0 hands. And before, there were at least some hands. So one of the nice things, inferring a schema from CSV data is not that impressive, right? But inferring a schema from JSON records is kind of impressive because that shit is terrible. And so one of the nice things that the SQL context can do in Sparc is it can go and it can dynamically sample the records, figure out what the variance is, and then sample a bunch more records and tell you what the schema of your data probably is. This is really useful when you have terabytes of logs generated by people who have long since left your company, or alternatively generated by people who will not respond to my emails. So we're going to load some CSV data, but if we were loading something that required a bit more complexity, it's really nice that Sparc can also handle that. It can handle a whole bunch of different things, including Google Bigtable. Give us money. There's a bunch of things built in. Your data is probably in one of these supported formats. If it's not, I found that going to vendors and asking them to add support for whatever it is I want to do is a pretty easy sell because you just threaten to leave. And vendors like it when you keep using their data formats. This is non-continuous. Okay. Anyways, clicky things. Okay, we're going to train a decision tree on genuine big data, about 50 kilobytes. So we've done step 1. You'll probably want to swap step 1 out with some big data that is relevant to your business. And now we're going to do step 2, which is data prep. And Spark actually has a bunch of different features for doing data preparation. And let's sort of look at a really, really simple pipeline in Spark. So how many people have used scikit-learn? Are there less people than I hoped? Okay, so Spark ML pipelines essentially are the stealing of the scikit-learn API and re-implementing it poorly on a distributed system. And so Spark ML pipelines, you can think of these being the different things that are happening. So we've got tokenizer, hashing TF, string indexer, and naive Bayes. And you'll notice some of them are colored blue and some of them are colored red. And the blue ones are what we call transformers. And transformers don't have to be fitted. And our estimators are colored red, and they have to be fitted to our data. And pipelines are Spark's idea that you should be able to put a bunch of these together and then just ask Spark to fit the entire thing for you, so you don't have to worry about fitting each thing individually and wondering what's going on. Conveniently, it also allows us to do things like if we had a bunch of different parameters on different things in here, we can do a parameter grid search across them and do some cool parameter tuning. I don't know if I'm running out of time, but whatever. So here's our really simple pipeline. We're going to start with many of the same things. We've got a bucketizer in here as well. I feel really bad that our examples are so similar. It makes it far too directly comparable, which is just super inconvenient. At least I didn't put in accuracy results in the end, so it's up to you to go and double check which one performs better. But once again, we're going to put things together in a vector. We're training a decision tree today, but it's really nice to know that there's a whole bunch of different models that we can look at, and I'll show you some of them. The feature ones that we've chosen are really basic, but there's about 30 different stages for doing feature preparation built into Spark, and then there's a whole bunch more that are just sort of generally available. So we have our fancy vector assembler. I'm going to look at these two parameters. Sorry, not two parameters. I'm going to look at these two inputs, and I'm going to put them together in this fancy thing called a vector. We're going to label our vector features. Once again, instead of casting true, false to an integer, Spark has this nice thing called a string indexer built in, which allows us to just take a field of strings and turn it into some numerical labels. There's also hashing TF, but string indexer will actually encode it like 0, 1, 2, 3. And so string indexer is an estimator because it actually has to see all of the strings to be able to assign them sequentially. And then pipelines are just you put all of your things together and then you ask Spark to fit them. And so here we've made a not very useful pipeline. So we take our pipeline of an assembler and an indexer and then we fit it. Yay! Yay? Yay! Okay, and there's a cat. Okay, so this is what our pipeline looks like. We take the input data, we assemble it, and then we take our input data and we turn our categorical information into IDs that I can actually use. And it's important to note that in Spark, all of these pipeline stages tend to just add columns. And this is because we might actually want to produce a bunch of synthetic features from the same input columns. So it doesn't automatically remove them. And this means that later on, when we're about to train our big fancy machine learning model, we might want to go ahead and throw out some of the data that we don't need anymore. Conveniently, that functionality is not built into Spark, but there is a third-party package that you can use. It's unfortunate. Yay, okay. Here's our example. Yay, okay, we're gonna make a decision tree. Decision trees are really simple. There's a whole bunch of parameters that we could fit, but I'm lazy. And you can look in the notebook if you wanna see actual parameters. But this is incredibly simple, and this can run on like a terabyte of input data. You would normally, instead of just fitting your decision tree at the end, you would just put it in a pipeline together with everything else you were doing, and then you can fit it, and then you can use the same pipeline model to predict on new inputs. Right, predicting the results, yay! Not super exciting, but yeah, we have kind of a shitty machine learning pipeline. You're probably about as happy as this cat, but you know, the low bar of the empty black screen earlier may have raised your expectations a little bit. So let's talk about cross-validation. I did not do very well in my statistics class. which is really not a secret anymore because I keep telling this to everyone in my talks. But like, my statistics classes we passed by the agreement that I wouldn't do statistics professionally, and now I do statistics professionally. And so cross-validation, we can use it to automatically tune our hyperparameters with really no basis in reality. This is a lovely way to overfit your models while telling yourself that you're not doing that. So if you're going to use cross-validation for tuning, please save a test set beforehand, because while cross-validation will tell you some accuracy numbers, if you use it for hyperparameter tuning, you've essentially trained on your test set. And you can get really good performance numbers when you train on your test set, but it probably won't generalize very well. You have to use Sparc above 1.4. That shouldn't be too hard. Sparc 2.2 is the latest version. We have this fancy example where if you're training naive Bayes, we can try a bunch of different values for this random smoothing parameter. I don't know what the smoothing parameter does, but I'm sure it does something interesting. I have a graph that implies it does. The graph is unrelated. But it's interesting because we can actually take this cross-validator and run it across our pipeline. And this means that, well, this example only shows you doing it to one stage in the pipeline and one parameter. We could actually do this on a whole bunch of different parameters. One of the things which I think is kind of neat to do is if you're considering buying a new data source, or like if it's worth it to have some new features integrated in, you can actually use cross-validation to change parameters that you might not be used to changing, like things like input column or the things that go into the vector assembler. And you can actually test to see if these parameters are actually, or if your new data or new features are actually improving your model, or just, are making you feel good about life. And so this can be a cool way to see if your stuff is actually good. If you don't want to know and you just want to deploy your stuff to production, no judgment, but please don't work in something that impacts my life. Right, so you might have said, Holden, decision tree classifiers are really boring. I want to raise a bunch of money in Silicon Valley. And I can't do that with a decision tree classifier, and I understand. There's a whole bunch of things that are built into Sparc. There's binary logistic regression, GBT classifiers, but none of them are cool. They're not deep learning. Deep learning is fancy. And so, the real answer for this is, if you want to do any of the really cool, fancy machine learning stuff, if you want to do deep learning and new research things, you can still follow this general model. You can still make an ML pipeline, do your feature prep in this way, but for your final model stage, you're going to have to go on the internet and take some code from some random grad student. But it's okay, because there's this flag that you can use to include code from random grad students. It's -- packages space com.gradstudentname : 0.0.0.1. And essentially, you can include arbitrary libraries. And many of these things, there's like an XGBoost library and some other things that implement this API, and you can actually try the different machine learning things from the different grad students and see which ones actually perform better. Normally, I spend most of my time trying to find one of them which doesn't crash, but once you find one, it's pretty good. Not that I have anything against grad students. They're lovely people, and they do a lot of my work for free. So there's also this project called Sparkling ML, which has this really fancy logo that I got made for $5 on the internet. And it's a panda, which is why I was so excited about pandas. Also, I love the pandas library. But one of the cool things which is happening in Sparc 2.3 is we're making it a lot faster to interact with Python code. And there's all of these really cool libraries in Python for doing sort of textual analysis, and a lot of us tend to have textual features, and so there's some interesting work happening, well, interesting work, I think it's interesting, to expose these these NLP tools into this pipeline interface so that people working in Scala can do some cool feature prep or processing of their textual data and include it with their like fancy deep learning library or decision trees if you just want your shit to work. Right, now this is probably the second most important slide. The next one has a link to a place where indirectly I make money. If this talk has not turned you off of Spark. There's a wide variety of books about Spark, and I'm going to do one of the things that authors don't normally do. I wrote this book. Don't buy it. I mean, you can if you really want. I will make about $1, but it's for Spark 0.7. And Spark doesn't look like this anymore. Instead, you should buy this new book where I get about $1.25. And that one's good. No, more seriously, if you're interested in Python, my friend Denny, Lee, and Thomas, I cannot pronounce his last name, wrote Learning PySpark. It's a really good intro. This says coming soon, but it's actually available now. I also owe him a 6-pack, so if you buy that, I probably don't owe him as much beer. I co-wrote Learning Spark with some of my, bosses at the time, and graciously they did not fire me for writing that book. So Learning Spark is another book, but mostly let's focus on the one where I make about $1.25. And this one is if you are interested in doing some really high performance stuff in Spark, if you're running into scaling challenges, or if you just want to help me buy a cup of coffee. Because, I mean, the Google money, you know, it's a hard life living in San Francisco working for Google. I mean, not at all. But that's cool. I'm going to be doing a bunch of things in places that are pretty far away. LinuxConf Australia is probably the closest, and I'm told they have really cute animals in their zoo there, and I want to go look at their animals. So if you want to come join me and talk about either open source or go on a trip to the zoo, you can come join me in Sydney in January. Alternatively, Strata San Jose, Strata Singapore just happened, but if you want to fly like 16 hours to come and listen to the same talks that were here, yeah, you can do that. And if there's other things that I should be knowing or doing, like let me know, and I don't mind flying for 16 hours that much. So just ping me and I will come. There doesn't seem like there were a lot of Spark users, but for the ones who are in the house, I'm always trying to get people to test their Spark code more, because a large number of people deploy machine learning code into production with no testing, and this makes me sad, and I'm pretty sure we're all going to die one day because of a project that I've been working on. So please tell me how you test your code, so I can tell other people how to test their code, and we can make things less terrible together. If there's any really interesting Python users in the house, I have this bit.ly link where I'm trying to collect UDFs from people. Right now, all of the performance benchmarks that I do are just kind of weird bullshit numbers that I make up. If you want my performance benchmarking to be more related to your workloads, you can share your UDFs with me, and then maybe your code will get faster instead of word count. The default is just we optimize word count, and that's not very useful. And that is pretty much it. Thank you all for sticking with me through all of the AV issues and the interpretive dance section of tonight's presentation. Yeah, sure. If there's any questions, I'm happy to take them. Are there any questions? Okay, cool. Yeah, so this is, the default is fourfold cross-validation, but you can, there's parameters that you can set if you don't want fourfold cross-validation. There's leave one out, but leave one out takes way too long. But yeah, you can tune this as you want. Thank you. That's a lovely question, and super awkward for me to answer. So the question was, when do you use TensorFlow and when do you use Spark? And I'm pretty sure there's someone in the back who's recording this. And I could be wrong. And so the answer is, I don't use TensorFlow. I work on Spark. But my coworkers work on TensorFlow, and they're lovely people too. I think TensorFlow is really great, and you can yell at me if I'm wrong, when you have a lot of data and you want to train something really cool or fancy. Or if you want to do something really interesting with images or one of the pre-canned models, TensorFlow really excels in that area. On the other hand, if you have like medium amounts of structured data, or if you're trying to do a relatively simple classification or regression problem, Spark really excels in those areas. I think Spark makes the most sense in the cases where it's not sort of a standalone machine learning problem, but it's part of something a little more complicated, like you have a large ETL job that's involved in getting your data in place. Would you yell at me? Okay, all right. I mean, this is like asking the Ford salesperson when to buy a Ford, and so my answer is going to be, you know, Spark is great. But like that's a pretty predictable answer, and you should go talk to the TensorFlow people so they can tell you that TensorFlow is great. And then between the two of us, you can pick whichever answer you want to do and tell your boss.
What's the future direction of Sparc?
Ooh. So the question is, what's the future direction of Spark? And that's hard to say. Spark is an open source project, and I am one of many people working on it. There are about 50 committers at different companies throughout the world. I think in the sort of like short term, there's a lot of really great work being done in both Spark streaming and Python accelerated Spark. There's also really interesting work being done in trying to connect Spark to TensorFlow and other fancy deep learning things that are not made by my employer, and therefore far less important. But really, I think, do you know about the Apache Arrow project? Or? Okay, cool. So Apache Arrow is really awesome, and it's from Wes McKinney and a bunch of people at 2 Sigma, and it's also actually an open source project that a lot of people work on, but Wes is the one who started it. And Apache Arrow is integrated into Spark 2.3, and it's sort of changing Spark from being a JVM-focused system into more inclusive and having more things perform well on Spark. So I think in a lot of ways, the future of big data in general, but also the future of Spark is very much a unification of systems, so that we can, do all of our cool stuff without having to copy our data between, 3 different systems. I'm a big believer in general purpose systems eventually eating the world, right? It's why we all drive kind of shitty cars. Wait, that was a bad example. But yeah, okay. If anyone wants like questions one-on-one that you don't want me to answer with like mostly jokes, you can come and just talk to me afterwards. Thank you all for listening.
Thank you very much, Holden, and thank you, Yufeng, for a very, very good talk, and thank you very much, guys. Hope that you take away more than just the cute animals from the slides. All right, we'll see you around, and have a good weekend. Thank you for being here.